Share screen. You guys see this all right? So yeah, it kind of comes down to, yeah, it kind of does come down to memorization. And so in order to break it down for you guys, there's these fancy German words or Russian, I don't know, but Markovnikov and Anti-Markovnikov, you really just have to know what they mean and what reaction applies to them. All right, so you have like these 8 different types of reactions, and when it comes down to it, you guys will realize that you know, with whatever substrate it may be, given what you're reacting with, will tell you the kind of reaction that's going to occur. All right, so like if there's something with mercury in it, you can have oxymurcuration. If you have a diatomic halogen like Cl2, then you're going to have halogenation. All right, if you have a boron, if you have like BH3, you're going to have hydroboration. All right, so there is telltale signs to help you figure this stuff out. So yeah, it's pretty similar to chapter 2, in which you kind of just have to know what things mean, and so you figure out, and so therefore you know what applies to what, and that will tell you how you get your product. So if you're adding, you guys remember what substituted means, right? If something is more or less substituted. All right, so that'll be your first major key to, I don't know why that's staying highlighted, but that'll be your first major key to this chapter, is knowing what side of the double bond is more or less substituted. All right, so with that in mind, let's go to a couple examples. All right, so HBr, all right, so a hydrogen with a halogen, it's in the name, right? Hydrohalogenation. All right, so you're going to be adding the Br to the more substituted side. All right, so in your studies, what I would recommend is one side of your flashcard, one side of your flashcard is,
anything from
no, I don't. I know what you're gonna say.
from where?
Chick-fil-A.
Hi, Mackenzie.
She's not on this one.
Oh, hi, class.
Oh shit.
Hi, guys.
Hi.
Oh, you don't want Chick-fil-A?
No.
Why? So good. Okay, love you.
All right.
You gonna watch Luna?
Yeah. All right, so yeah, one side of your flashcard will be your reagent, is what I recommend. So like HBr, what does that tell you? Flip the card over, you have hydrohalogenation, and that you're adding whatever it is to the more substituted side. All right, that's probably your best bet. All right? And that's kind of the rationale in order to figure out your products. So with that in mind, what side of the double bond will this Br be added to? The left or the right? The left. All right, so your product will look exactly like that. All right, that's it. All right, and can somebody tell me the reason why there wasn't a rearrangement in this? So your intermediate looked like this. Why wasn't there a rearrangement? Yeah, it's already tertiary, right? It's already about as stable as it can get. All right, so what happens mechanistically is a pi bond it's basically a acid-base reaction, right? You have a pair of electrons that will attack the hydrogen, and you will then have your halogen floating around, right? So your intermediate, if you have one, looks like this, right? So John's saying that there's a ring expansion. Does anybody else disagree, agree? Yeah, you're gonna have a ring expansion because in this type of reaction, that is one of the stipulations that can occur, right? So you're gonna create a new bond between these that's gonna break, and now you have this, right? And some could argue that you may have a hydride shift going that occurring here, but at the end of the day, now your electrophile can attack, all right? And the same exact thing is going to occur with an acid. What do you know about acids? They want electrons, right? A positive charge. Remember from cardio, your positive charge wants an electron, right? So your positive charge will get it from this pi bond. You're then going to have your intermediate. What's going to happen? Your OH from the water will be added to that more substituted side. So that is your product. And same goes for this one. Now, I believe, let me see. So this one, will we be adding the OH to number 1 or number 2? Number 1, right? Because that's the more substituted side of the double bond. And that's it. All right. Don't overthink it, guys. Right. So given an acid or given a H with a halogen, this reaction will occur, and thus these two statements are what you need to know. That's how I would study for it. All right. So like chapter 5 with these little tips and tricks, you can make this as easy or as hard as you want. All right. So kind of like in the name, you have something with mercury as your reagent. What type of reaction is going to occur? Oxymurcuration. Okay. So hopefully that's intuitive. And at the end of the day, you're adding OH to the more substituted side. So is the OH going to be added to number 1 or number 2? John says number 1. Does anybody else disagree? Agree? Yeah, it will be added to number 1, right? Because that's the more substituted side of the double bond. And you guys, it's weird. Do you guys want me to show you how you even get OH onto this, given all this other bullshit? All right. So what happens is that your pair of electrons from this pi bond do that, right? So they will bond to that mercury, and will look something like this. You have your OAC, right? That carbon is not stable, right? That water is going to come in, attack, right? So that's going to, one of these is going to fracture, right? I believe this one's going to break. You get this, which is your mercury group. You see OAC. All right. And the reason why it's called oxymurcuration, demercuration, is because this BH4 or i.e. any reduction agent, all right, that will eliminate that will remove that mercury group, and thus you're left with your major product. All right. Oh, shit. So this is how you're getting the mercury intermediate. All right. I've been tested on it before. I know I have a couple familiar faces, so they've probably seen it before. So I just wanted to make sure that I walk through how you're getting that mercury intermediate. Go fuck shit up. All right. 9-month-old beast. All right. So at the end of the day, what you end up with is the OH on the more substituted side. So your product for this one will simply reflect that, right? OH on the more substituted side of the double bond, right? Can we get by just by memorizing these stuff, or I recommend having some understanding of the mechanism, but it should make sense, right? It's kind of an acid-base reaction. You have your pi bond that has a pair of electrons attacking or being bonded to your reagent. And so you have something going on there, and thus something is being added, right? So in essence, if you guys haven't caught on yet, it's basically the reverse of chapter 7. All right. But so far, any questions, comments, concerns? Are you guys good? I'm assuming you guys are good. All right. So halogenation. Kind of in the name, can somebody tell me what they think the reagent's going to look like? We had hydrohalogenation before, which was a halogen with a hydrogen. What's this one? What will this one look like? Yeah. So it will be a diatomic halogen. All right. Anything with that will be a halogenation. And so this is still following the Markovnikov Russian/German, I don't know, rule, which means it's adding to the more substituted side. But really, you're just adding your halogen to each side of the double bond. All right. So your product will have this. And the stipulation that you may have to remember with this one is that your halogens are adding anti. Now, if you're adding things anti, what do you guys think that means? Yeah, they're adding in the opposite direction. If they're adding in the opposite direction, another way of thinking about it is just trans, right? That's it. All right. And he may try to throw you guys off. He's usually pretty fair, but you guys should know from chapter 5 that a single bond can rotate. And thus, if you rotate about that double bond, do you guys see how you get this? So just be wary, all right? These two are the same thing. All right. So this one is pretty self-explanatory. All right. But another thing you have to look out for, if you have your diatomic halogen, thus halogenation, but you have water floating around as well, instead of 2 halogens being added, you're going to have 1 halogen and 1 OH being added. All right. And the only thing you have to know about that is your OH will prefer the more substituted side. All right. So your OH, let's just, again, because we're adding anti, let's just say that is dashed, and thus our Cl must be added wedged. All right. This makes sense? Any questions? You guys good? All right, so if you have your diatomic halogen, it's halogenation. But if you have your diatomic halogen with water, then you're going to add a OH as well, and that OH is going to prefer the more substituted side. That's the only thing. All right. All right, hydroboration. I mentioned it before. What do you think the reagent may look like? Yeah, there's going to be a boron around, right? So what's going to happen is you get some weird intermediate. Looks all complicated. But really, it's not when you break it down. All right. So you have an OH being added to the less substituted side, but your intermediate looks something like this, right? Your borane, right? You added your hydrogens, right? So that's your alkyl borane intermediate, all right? Now, what happens is that your other reagents will come in and slice off that borane, and you replace it with your OH. Thus, all that you're left with is OH being added to the less substituted side. All right. And the reason why I showed this, if you've looked at the handout, it's in files, is I've seen him test on it before, kind of like that mercury intermediate. He may test you on this intermediate as well. All you have to do is simply, he may ask you to go backwards, all right? And what you have to do is, all you have to do is simply, say for this one, is slice that bond where the borane is directly attached. Your double bond is right there. Thus, that is what you started with. If you slice, again, with this one, you break that bond, add your double bond. You guys see how that is what you started with. So kind of like this intermediate, slice off where that borane is attached, add your double bond. What do you get? What you started with. All right. That makes sense? Everybody good on that? All right. Dihydroxylation. In the name, based on the name, what do you think is going to happen? What's a hydroxyl? What's di mean? what do you think is going to happen? You're adding two OHs, right? And all that you're doing is you're adding an OH to each side of the double bond. That's all. And it adds syn, right? I believe the other example was anti, but we're adding syn. And so you could be both wedged or both dashed. Let's just say both dashed. Right? Thus, your methyls be wedged, right? That's all. Right? So your common reagent will be this, but just keep in mind that cold, emphasis on cold, cold KMNO4 can have this occur as well, right? Because we're going to see now that hot KMNO4 will do ozonolysis. And in the name, what reagent will you commonly see for ozonolysis? Ozone, right? Ozone. So all you have to do is act as if you split that double bond in half. So here's one side of the double bond. Here's your other. You split it in half, right? All you have to do, add an oxygen. Those are your products. All right. Can somebody tell me what functional group that is? I'm holding out hope. In green, what's that functional group? You guys are still going to have to know functional groups for the final. It's going to come back and bite you in the ass if you don't know them. What is that functional group in green? Does anybody know? If not, just say so. Yes, it's an aldehyde. Because we know that a ketone has two R groups coming off of that carbonyl, right? Your carboxy has an OH coming off of that. Your aldehyde has just a hydrogen coming off of it. So be wary. Remember your implied hydrogens, all right? So moving on, split in half. All right, so there's part of one. And here we're going to have another. Someone mentioned reduction, and that is a good point in this. Does anybody know if methyl is a oxidative or a reduction agent? A methyl, just carbon with hydrogens. Anybody know? Yeah, we know if something is being oxidized, it's either removing hydrogens or it's adding oxygens, right? Methyl isn't adding many hydrogens, right? There's nothing for it really to add. This is your species that's adding your oxygens. So here, if you have your dimethyl, it's going to be a reduction, and thus you're creating just an aldehyde. Here is oxidative. So not only are you going to create a carbonyl, but you're going to create a carboxylic acid. All right. That's the difference between these two ozonolysis. All right. So yes, here's your two products for your ozonolysis. Of course, one of them is major, one of them is minor, but that's how you get them. All right. Another thing, another reduction agent that you may see is something like zinc oxide. All right. That will do the same thing as that. All right. So someone in my previous section thought this was super confusing. Is there anybody here that's confused on how we're getting this product? Or are you guys good? Confused a little on the second one. So this ozone with this dimethyl, remember Me is just methyl, will be creating this aldehyde, right? Doing the same exact thing. You're acting as if you're breaking that double bond in half and you're adding an oxygen. But because this reagent here, instead of them being methyls, this one is oxidative. So it's going to not only add an oxygen, it's going to add an OH, creating a carboxylic acid. That's the major difference between the two. All right. So you guys remember, can somebody remember from chapter 7, I mentioned that if you have an acid like this, can somebody tell me if there's going to be a rearrangement or not? Where I said, if you have something like HS2SO4 or H3PO4, you're probably going to have an E1 reaction if you're removing an oxygen, if you're removing an OH. If you're doing the reverse, you still have a rearrangement that can occur, right? That's why 2 is our answer, because when you, again, it's, again, an acid catalyzed. That H2SO4 is an acid. So an acid catalyzed, you're going to have that intermediate, right? So that, and why is 2 our answer? What happened here when we did our intermediate? Yep, you had a ring expansion, right? That's how you got 2. And then your OH can be added, right? So it's simply that first type of reaction that we did, all right? This one, I'm pretty sure I got wrong when I took the class, all right? So it can be super confusing, but it's simply a 2-step process, all right? So the first step is what? Does anybody remember what D means? Other than what we often use it as today? Deuterium, right? It's just acting as a hydrogen, right? So BH3 really is what? What type of reaction? What did we say that was? Yeah, you have hydroboration, right? So you have your, again, less substituted side. So you have your boron intermediate here. All right, and typically with hydroboration, it would be replaced with a OH, right? Somebody give me a yes or no. Typically in hydroboration, that boron intermediate will be just replaced with a OH on the less substituted side. All right. So the thing with this one is that we have an extra step. This here is acetic acid. This here has a carboxylic acid. This carboxylic acid will simply strip that OH away. That's all it's doing. That's why you're left with A. All right, and what do we know about hydroboration? The directionality. Hydroboration. It's adding sin, right? It's adding sin. So just going back. So say you added your hydrogens dashed. In this case, your hydrogen is D. Right? You're adding sin. Typically, this would be your product, right, for hydroboration. But that acid, that acetic acid comes along and takes away that OH. Thus, you're left same exact thing, just without the OH. That's how we got A. All right? Is that somewhat understandable? All right, so again, that's if you have something like a carboxylic acid instead. Typically, you're going to see hydroboration with peroxide, in which you're simply adding your OH to the less substituted side. But if you have it with that, something like a carboxylic acid, that's what's going to occur. All right, so just wanted to make sure I went over that. All right, so Cl2. So anybody remember, does halogenation add syn or anti? So let's go check. Halogenation. Halogenation, it adds anti, right? So one of them is going to be wedged, one of them is going to be dashed. That is why this does not create a meso compound, right? You guys see that? So if one's wedged, one's dashed. We tried to draw a plane of symmetry. Are these two sides mirror images? No. So that's why it doesn't create it. That's why this type of reaction does not create a meso compound. That's all. All right. And another thing that he may choose to throw at you is cycloproponation. So what do you think in the name would happen? Cycloproponation. What do you think you're going to make? Yeah. So what may often occur is if you have something like this, CH dihalogen, all you're simply going to do on like this with your two halogens. All right. So this is what we call cycloproponation. All right. Yeah. And another key point that I would remember is that this reaction occurs with something called a carbene divalent. All right. Carbene divalent. Right. So what that is this. All right, it could be hydrogens. In this case, it was halogens. All right, carbene divalent. So what happens is that you have your double bond. All right, you have your double bond, and this is what occurs. All right, this lone pair comes and attacks, and this lone pair attacks that hydrogen. That's how you get this creation here. All right, so this is cycloproponation. Right, it's in the name. You're creating a cyclopropyl just on where that double bond was. All right. Any questions, comments, concerns? Any questions, comments, concerns? Are you guys good? All right, so hopefully that cleared up some stuff. Hopefully it made it easier for you guys. In summary, we went over all the types of addition reactions you're going to see in this chapter, how you do them, again, just in your studies. If, okay, given your reagent, then you know what type of reaction is going to occur, and thus you just need to know what type occurs via what. And here on that first page, I summarized that. All right. So feel free to use that handout at your leisure. It's under files. And that is all I have for you today. All right. Thank you, you too.
Hello.
Yeah, what's going on?
I had a question because I was trying to get on the break room earlier today, and I got in, but it wasn't on the Zoom. Is there a reason for that? I went through a link and I tried going on Zoom to get on it. But
I made sure to mention it in the beginning of the semester, is that I don't know how Canvas did it, but I always created and posted all the information needed on my discussion posts. So if you guys just keep up with my discussion posts, week 1 through 8 now.
yeah.
I also included the link and joining information. I've always had.
Yeah, I noticed that in the discussion post, but I usually prior to this week, I would just go through the camp. I'd click on Zoom and then I click on upcoming and it would just come up.
Yeah, I didn't know that was a thing. I never did that. So I never intentionally created any Zoom tab or anything like that. So it must have done it on its own. And so, yeah, the much more reliable way has been just, again, like I mentioned, just using that access info that I've always had. Because previously, the reason why I send out that info is because over summer and when COVID started, that people had this bullshit tech stuff. So,
so
yeah, I'd always have made sure to send out that info.
All right, thank you.
Yeah, no problem.